in progress.
In this class, let us discuss about galvanic cells, which comes under electrochemistry. So in our daily life, we are very much dependent on batteries. We need battery for mobile, remote control, UPS, vehicles, toys, etc. So these batteries, they are based on the principles of electrochemistry. Electrochemistry involves interconversion of electrical and chemical energies. In electrochemistry, we come across mainly two types of cells: galvanic cells, electrolytic cells. In galvanic cell, chemical energy is converted to electrical energy. Certain chemical reactions are used to produce electric current. Electric current is produced in a galvanic cell. In electrolytic cell, electrical energy is converted to chemical energy. So in electrolytic cell, electric current is used up, consumed to make certain reactions happen. So before going ahead, in this class, we'll be discussing mainly about galvanic cell. And before going ahead, let us first recap the basics. So the entire electrochemistry is based on redox reactions. It involves redox reactions. So what is a redox reaction? Redox reaction is a reaction in which both reduction and oxidation take place simultaneously in the same reaction. So for example, zinc reacts with copper sulfate solution to form zinc sulfate solution and copper. So in this reaction, zinc loses 2 electrons and is converted to zinc 2 plus in zinc sulfate. Loss of electrons is oxidation. So zinc is oxidized to zinc 2 plus. In copper sulfate solution, there is copper 2 plus ions. The copper 2 plus ions gain electrons. So copper 2 plus ion gains 2 electrons and is reduced to copper. Gain of electrons is reduction. So in this reaction, both reduction and oxidation are happening. So it's a redox reaction. Further, it is a spontaneous reaction. What is a spontaneous reaction? Spontaneous reaction is a reaction which can take place by itself or at least continue by itself. It doesn't require any external aid. It can take place entirely by itself, or it may require external aid only for initiation and can continue by itself. So such reactions are called as spontaneous reactions. So when I bring zinc in contact with copper sulfate solution, the reaction starts. I don't have to provide any heat or any other kind of energy. So the reaction, as soon as zinc is brought in contact with copper sulfate solution, the reaction will take place by itself. Okay? So this is a spontaneous reaction, and then it's a redox reaction. So it's a spontaneous redox reaction. Another example for spontaneous redox reaction is, say, sodium reacts with chlorine to form sodium chloride. So here sodium is oxidized from 0 to +1 oxidation state. So in sodium chloride is an ionic compound containing Na plus and Cl minus. So sodium is oxidized to Na plus and chlorine is reduced to chloride. And this reaction is spontaneous. So it is spontaneous redox reaction. Then what is a non-spontaneous redox reaction? So non-spontaneous redox reaction, it is a redox reaction. It involves both reduction and oxidation, and it is non-spontaneous. That is, it cannot take place by itself. It requires constant external aid. So it cannot happen by itself. So for example, sodium chloride. Sodium chloride is the common salt which we use in our kitchen. So it is highly stable. It will not decompose by itself. It won't decompose to sodium and chlorine. But it can be made to happen when we provide electric current, when we pass electric current through molten sodium chloride. So it gets decomposed to sodium and chlorine. But in between, if we stop the supply of electric current, the reaction will stop. So it needs external aid, external energy, not just for initiation, but throughout the reaction, external aid is required. So once we stop the external aid, once we stop the supply of electric current or external energy, the reaction will stop. So such a reaction is non-spontaneous reaction. It cannot take place by itself. It requires constant external aid throughout the reaction. Such a reaction is non-spontaneous reaction. So another example is reaction of nitrogen with oxygen to form nitric oxide. So fortunately, this is a non-spontaneous reaction. If it were to be spontaneous, then we would not be left with any oxygen in the air. So this is a non-spontaneous reaction. So the reaction will not take place by itself. So the reaction will take place only when we heat this mixture of gases to high temperature. So if we stop heating, the reaction will stop. It cannot continue by itself. It cannot happen by itself. So these are non-spontaneous redox reactions. So in galvanic cell, we'll come across spontaneous redox reactions. In electrolytic cells, we'll come across non-spontaneous redox reaction. So in this class, we'll be discussing about galvanic cell. So we'll be discussing mainly about the spontaneous redox reactions. Okay, so now let us again look at this reaction. Zinc with copper sulfate to form zinc sulfate and copper. So in this reaction, zinc is losing 2 electrons and is oxidized to zinc 2 plus. Copper 2 plus gains 2 electrons and is reduced to copper. Or you can say there is a transfer of electrons from zinc to copper 2 plus. Zinc loses 2 electrons, copper 2 plus gains 2 electrons. So we can say there is a transfer of electrons from zinc to copper 2 plus. Now, what if we can make this transfer of electron from zinc to copper 2 plus happen through a metal wire? If we make the transfer of electrons from zinc to copper 2 plus happen through a metal wire, then we would be generating electric current. Okay, then how to do this? So this is possible in what is known as a galvanic cell. So this is one example of a galvanic cell, one illustration example of a galvanic cell. So here we have zinc rod. So in the zinc rod, zinc atoms, some zinc atoms, they lose electrons. They leave behind electrons in the zinc rod and go into the solution as zinc 2 plus. Some zinc atoms, they lose electrons, leave behind electrons in the zinc rod, go into solution as zinc 2 plus. So these electrons move through the metal wire. They move through the metal wire. They come to the copper rod. The electrons come to copper rod. So at copper rod, now in the solution, there are copper 2 plus ions. So these copper 2 plus ions gain the 2 electrons at the copper rod and get deposited as copper atoms on the copper rod. So in this way, electrons are transferred from zinc to copper 2 plus through a metal wire. Once electrons are moving through a metal wire, then that would be producing electric current. Okay, so this is a galvanic cell. Galvanic cell is a device in which a spontaneous redox reaction, such as this is one example. There are many other examples. So galvanic cell is a device in which a spontaneous redox reaction is used to produce electric current. So here in the galvanic cell, we have in this part, oxidation is taking place. Zinc loses 2 electrons and is oxidized to zinc 2 plus ions. Zinc atoms in the zinc rod, zinc atoms lose 2 electrons and go into the solution as zinc 2 plus ion. So oxidation is taking place. So this part is called as oxidation half cell. So why it is called oxidation half cell? Now this whole thing is galvanic cell. This entire thing is galvanic cell. And in this part, the oxidation half reaction is taking place. So it is oxidation half cell. And on the other side, on the right side, so in this part, reduction is taking place. Copper 2 plus ions gain 2 electrons at the surface of copper rod and get reduced to copper. So reduction is taking place. So this part is reduction half cell. Why it is half cell? Because here the half reaction, reduction half reaction takes place. So a galvanic cell consists of 2 half cells. of which one will be an oxidation half cell where the oxidation process takes place, and the other is a reduction half cell where reduction takes place. So now what is a half cell? So a metal dipped in metal rod or metal strip or metal bar dipped in aqueous solution of its salt is called as half cell. So for example, silver strip in silver nitrate solution, it will be a silver half cell. Magnesium rod in magnesium chloride solution will be a magnesium half cell. So in the half cell is metal rod dipped in aqueous solution of its salt. In the half cell, the metal rod that has been dipped in the solution, that metal rod, that is referred to as electrode. That is the electrode. And aqueous solution of salt of the metal, that is the electrolyte. That is called as electrolyte. Okay, so now what happens when we dip a metal rod in aqueous solution of its salt? What happens in a half cell? So two processes happen simultaneously. Two processes happen. We look into these processes one by one. So in one process, few metal atoms, not many, very few metal atoms on the metal rod. On the metal rod, very few metal atoms. They lose electrons. They leave behind electrons in the metal rod and go into solution as positive metal ions. So on the surface of the metal rod, few metal atoms, they lose electrons, leave behind electrons in the metal rod and go into solution as positive metal ions. So here there is loss of electrons. So this is a oxidation. This process is oxidation. The metal is oxidized to metal ion, positive metal ion. Now simultaneously along with this, another process also takes place. So now few metal ions, some metal ions which are already there in the solution because the solution is aqueous solution of salt of the metal. So some metal ions which are already there in the solution, they gain electrons at the surface of the metal rod. They gain electrons at the surface of the metal rod and get reduced to metal atoms. So those metal atoms get deposited on the metal rod. Few metal ions which are already there in the solution gain electrons at the surface of the metal rod and get deposited as metal atoms on that metal rod. So here the metal ions are getting reduced to metal. Gaining electrons is reduction. So here reduction is taking place. So we can look at process 1, process 2. Process 1 is oxidation, process 2 is reduction. And if you look at the equation, we can easily see that one process is the reverse of the other. So the two processes, they are a pair of reversible process. And so an equilibrium will be attained between the two processes. An equilibrium will be attained between the two processes. So we discussed that in a half cell, two processes take place. In one process, it is oxidation. Metal atoms get oxidized to metal ions. In the other process, it is reduction. Metal ions from the solution get reduced to metal atom. Now, if these two processes happen to the same extent, then there will be no net change. If the two processes take place to the same extent, there is no net change. Say, for example, 5 metal atoms get converted to 5 metal ions, and simultaneously 5 metal ions get converted to 5 metal atoms. There will be no net change. But in case of metals like zinc, the first process happens to a greater extent than the second one. So in case of metals like zinc, more of oxidation takes place. So by the time equilibrium is reached, before equilibrium is reached between the two processes, relatively more number of metal atoms on the surface of the metal rod would leave behind electrons, the valence electrons on the surface of the metal rod and go into solution as positive metal ions. So more of oxidation would have taken place, and by the time equilibrium is reached, there would be a net negative charge on the surface of the metal rod. The negative charges on the surface of the metal rod will attract positive ions in the solution. So negative charges on surface of the metal rod attract positive ions in the solution, giving rise to formation of a electrical double layer. Electrical double layer. So there's a layer of negative charges on the surface of the metal rod and a layer of positive charges in the solution close to the surface of the metal rod. So this is what happens in case of metals like zinc. In case of metals like copper, more of reduction takes place. The second process happens to a greater extent. More of reduction takes place in case of metals like copper. So that is relatively more number of copper 2 plus ions present in the solution. They gain electrons at the surface of the metal rod and get deposited as metal atoms on the metal rod. So since more of metal ions add to the metal rod, they gain electrons at the surface of metal rod and get deposited as metal atoms on the metal rod. So by the time equilibrium is reached, there will be a net positive charge on the surface of the metal rod. The positive charges on the surface of metal rod will attract negative ions in the solution, giving rise to electrical double layer. So there's a layer of positive charges on the surface of the metal rod and a layer of negative charges in the solution close to the surface of the metal rod. So again, electrical double layer is formed. However, in both cases, what we see is that the sign of charge on the surface of the metal rod is opposite to the sign of charges in the solution. Sign of charge on surface of metal rod is opposite to sign of charge in the solution. So there is a potential difference between the metal rod and the solution. Now the metal rod is the electrode. It is referred to as electrode, and the solution is electrolyte. In both cases, the metal rod is electrode, the solution is electrolyte. So there's a potential difference between electrode and electrolyte. This is known as electrode potential. So what is electrode potential? It is the potential difference between electrode and electrolyte. Now when the half cell is under standard conditions, then the electrode potential is referred to as standard electrode potential. So standard electrode potential is the electrode potential of a half cell under standard conditions. So what are the standard conditions? The concentration of the electrolyte must be unity, 1 molar with respect to each participating species. Temperature must be 298 Kelvin and pressure must be 1 bar. So then the half cell is said to be under standard conditions, and in such a case, the electrode potential will be standard electrode potential. Now we discussed that in case of metals like zinc, more of oxidation takes place. So the respective electrode potential is oxidation potential. So for zinc, the oxidation potential is plus 0.76 volt. Oxidation potential corresponds to the oxidation reaction, and it is a measure of tendency for oxidation. Okay, so now in case of metals like copper, more of reduction happens and the respective electrode potential is a reduction potential, and reduction potential corresponds to reduction reaction. It's a measure of tendency for the reduction reaction. So in case of some metals, it is oxidation potential. For some metals, it is reduction potential. Then how do we compare the electrode potentials of different half cells? So for this, the IUPAC has recommended that we should consider the standard reduction potential as the standard electrode potential. That means we have to consider the reduction potentials of the different half cells for comparing them or for calculations. So in case of copper, we have the reduction potential plus 0.34 volt. But what about zinc? So zinc, here we are having oxidation potential. So reduction potential is simply the negative of oxidation potential. Reduction potential is minus of oxidation potential. So oxidation potential for zinc is plus 0.76 volt. Therefore, reduction potential would be minus 0.76 volt. Oxidation potential corresponds to oxidation reaction, Reduction potential corresponds to reduction reaction. Okay, so similarly in case of copper also, like here we have reduction potential of copper 0 plus 0.34 volt. So oxidation potential would be minus of reduction potential. So oxidation potential for copper would be minus 0.34 volt. However, as per the IUPAC recommendation, we shall discuss only about the reduction potentials. So even if we mention electrode potential in this class or in general in any textbook, unless otherwise mentioned, when they say electrode potential, they are particularly referring to the reduction potential. So from now onwards, we'll discuss only about the reduction potentials. Okay, so now with this background, we are ready to understand the construction and working principle of a galvanic cell. So this is one example. What is illustrated over here is one example of a galvanic cell. This is made up of zinc half cell and copper half cell. So such a galvanic cell, which is made up of zinc half cell and copper half cell, is called as Daniell cell. We can make numerous galvanic cells by combination of different half cells. Okay. So now let us discuss taking this Daniell cell as an example. Okay, so in this galvanic cell, it is made up of two half cells, the zinc half cell and copper half cell. In zinc half cell, more of oxidation takes place. So it is the oxidation half cell. Copper half cell, more of reduction. So that is a reduction half cell. Okay. So we have two half cells. The two half cells are connected externally by a metal wire. The metal wire connects the electrodes of the two half cells. And in between the metal wire, we have a voltmeter, so we can note down the voltage of the current produced. Then the two half cells are connected internally by a salt bridge. The salt bridge connects the solutions of the two half cells. So now what is this salt bridge? So salt bridge is a U-shaped glass tube. It is a U-shaped glass tube in which a suitable electrolyte such as potassium chloride solution or potassium nitrate solution has been jellified using a polysaccharide called agar-agar. So this potassium chloride solution is taken in the form of a gel in this U-shaped glass tube and it is inverted. So one limb is placed in the copper sulfate solution, the other limb in the zinc sulfate solution. Now, what is the role of this salt bridge? So salt bridge, it electrically connects the solutions of the two half cells. It electrically connects solutions of the two half cells. So this is very much necessary to complete the circuit. And salt bridge connects the solutions of the two half cells without allowing the solutions to mix up. Without allowing solutions to mix up. So this is one role of the salt bridge. Then further, it balances, the salt bridge balances excess charges developed in the solutions. So during the process, some charges will be developed in the solutions. That excess charges will be neutralized by supply of oppositely charged ions from the salt bridge. So the salt bridge will balance the excess charges, balance or neutralize the excess charges developed in the solutions. So this is the role of the salt bridge. It electrically connects the solutions of the two half cells without allowing the solutions to mix up and then balances or neutralizes the excess charges that develop in the solutions. So this is about the construction of the galvanic cell. Now let us see how does it work? How is the electric current produced? So in zinc half cell, more of oxidation takes place. So it is the oxidation half cell. So On the surface of the zinc rod, zinc atoms lose electrons. They leave behind electrons and they leave behind electrons on the zinc rod and go into solution as zinc 2 plus ions. So since the zinc atoms, they leave behind electrons in the zinc rod, so the zinc rod becomes negatively charged. So this electrode, it is a negative electrode. So in this example, the zinc rod is negative electrode. And by standard definition, the electrode where oxidation takes place is called as anode. So here the zinc rod is an anode. It's a negative electrode. It is an anode. And by convention, when we symbolically represent the galvanic cell, so there is a method for symbolic representation of galvanic cell. So when we symbolically represent galvanic cell, we represent the oxidation half cell on the left hand side. By convention, the oxidation half cell is represented on the left hand side. So this electrode, the zinc electrode, is also a left hand electrode. So in this example, the zinc electrode is an anode. It is a negative electrode. It's a left hand electrode in this particular example. Okay, so now what is happening in the solution? So in the solution, so since zinc atoms from the zinc rod, zinc atoms, they lose electrons, come into solution as zinc 2 plus ions. So in the solution, there'll be excess zinc 2 plus ions, or there'll be excess positive charge in the solution. The excess positive charge in the solution is balanced by supply of negative ions such as chloride ions from the salt bridge. So anions or negative ions such as chloride ions from the salt bridge move into the zinc sulfate solution and balance the excess positive charge. So this is what happens on the left hand side. Now let us see what happens on the right hand side. So on the right hand side, we are having the copper half cell where more of reduction takes place. So it is a reduction half cell. So copper 2 plus ions in the solution, they gain electrons at the surface of the copper rod and get reduced to copper atoms. So these copper atoms get deposited on the copper rod. Copper 2 plus ions gain electrons at the surface of the copper rod and get deposited as copper atoms on the copper rod. So since the positive ions, copper 2 plus ions are adding to the copper rod, so the copper rod becomes positively charged. So in this example, the copper rod is a positive electrode. And so it is a positive electrode. By standard definition, the electrode where reduction happens is called as cathode. Cathode is the electrode where reduction takes place. And by convention, in the symbolic representation of galvanic cell, the reduction half cell is represented on the right hand side. So this is a right hand electrode. So in this example, the copper rod is a cathode, it is a positive electrode, or it is a right hand electrode. Now what is happening in the copper sulfate solution? Now since copper 2 plus ions, they gain electrons and get deposited on the copper rod, there will be a shortage of copper 2 plus ions in the solution. There will be a deficit or shortage of copper 2 plus ions in the solution, or we can say there will be unbalanced sulfate ions in the solution, or we can say unbalanced sulfate ions in solution means, so there will be a net negative charge in the solution. So the negative charges in the solution will be balanced by supply of positive ions such as potassium ions from the salt bridge. So positive ions or cations such as potassium ions from the salt bridge will move into the copper sulfate solution and they balance the excess negative charge. Okay. So now the zinc rod is negatively charged, the copper rod is positively charged. So there is a potential difference between the zinc rod and copper rod. So electrons will start flowing from zinc rod to copper rod through the metal wire. Okay. So once electrons are flowing through the metal wire, so electric current is produced. So in this way, electric current is produced in the galvanic cell. So we have included a voltmeter. So we can using the voltmeter we can note down the voltage of the current produced. So in general, electrons flow from anode to cathode. So here the zinc electrode is the anode and copper electrode is the cathode. In general, in any galvanic cell, electrons flow from anode to cathode. Electrons flow from anode to cathode. This is true for any galvanic cell. Now, by convention, the direction of flow of electric current is opposite to the direction of flow of electrons. Therefore, we say electric current flows from cathode to anode. Electric current flows from cathode to anode. So electrons flow from anode to cathode. Electric current flows from cathode to anode. So this is how galvanic cell works, and this is how current is produced using a galvanic cell in a galvanic cell. So here in the zinc half cell, the oxidation takes place. In the copper half cell, the reduction takes place. So let us look at the equations. So at the anode or oxidation half cell, so the oxidation half reaction takes place. Zinc is oxidized to zinc 2 plus. At cathode, the reduction half reaction takes place. Copper 2 plus is reduced to copper. If we add the two half equations, we'll get the equation for the overall reaction. So the equation for the overall reaction is simply zinc reacting with copper 2 plus to form zinc 2 plus and copper. So this is same as zinc reacting with copper sulfate solution to form zinc sulfate solution and copper. Only difference is if I react zinc directly with copper sulfate solution, so there will be direct transfer of electrons from zinc to copper 2 plus, and both oxidation reduction they'll be happening simultaneously, and together they'll be happening. Of course, over here also oxidation and reduction in galvanic cell also oxidation reduction happens simultaneously, but they are separated. So oxidation half reaction happens in the oxidation half cell, reduction half reaction happens in the reduction half cell. So this was about the construction and working principle of a galvanic cell. Hope this helps you, and thank you.